completed her MTech in computer science at the same institution. Before joining IIT Indore, she served as an assistant professor at the Indian Institute of Information Technology, Guwahati. Her research interests include services computing, artificial intelligence, machine learning, automated reasoning, formal methods, and related fields. So this was all about ma'am. So once again, on behalf of Aderia Global Institute of Engineering and Management, join me in extending a warm welcome to Dr. Somi. Look forward to gaining insight into her wealth of knowledge and experiences on deep learning. Now I request Dr. Somi to enlighten us with her words. Thank you, ma'am. Please go ahead.
Thank you for the introduction. So, shall I share my screen?
Yes, ma'am.
Okay. Can you see my screen? Is it visible? Hello. Am I audible? Can you see my screen? Can you confirm me? Okay, okay,
Yes,
fine.
madam. It is visible.
So, okay, okay, fine, fantastic. Okay, so let me start today's session. So once again, thank you for the introduction. I am Shomi Chattopadhyay from IIT Indore, and today's topic is QS aware service recommendation using deep learning. So this is the overview of what we are going to cover today. First, I am going to introduce the domain of services computing and what is the research scope in the domain of services computing. And I'll try to introduce the preliminaries of what is necessary to know in order to understand the services computing. Then we will see the literature which is existing for the services computing for service recommendation mainly, for QS prediction, various modeling, various solutions, and then different challenges. Next, we are going to discuss one of our proposed framework, which is anomaly resilient real-time QS prediction framework with graph convolution. As I see that the main concern of this FDP is this deep learning part, deep learning in emerging fields. So I thought it would be a great idea to discuss this graph convolution network on this service recommendation. And then we will discuss a few of our experimental results and followed by conclusion. With the proliferation of this advanced network technology and automated system, and day after day, we are getting different set of smart devices. And nowadays, everyone is having the smart devices, and that is enabling us to use different online activities. And that is why the number of online activities are increasing exponentially. And to satisfy the market demand or users demand, the number of web applications and the softwares are increasing nowadays, and this frequent addition of this functionally equivalent services lead us to the area of this service recommendation actually, because the number of functionally equivalent services, when it is increasing rapidly, then there is a deciding factor which comes into the picture, which service we are going to choose and why we are going to choose that particular service. Now, this service recommendation model, this actually, the services can be recommended based on various criteria. So it depends on what kind of model we are going to use. Sometimes we are going to use business to business model or business to customer model. So depending on this thing, actually, we can have importance on the cost of the service, the quality of service parameters, the features a service is providing, or the feedback which user is giving on different set of services, or the different preferences based on which actually we need to do the recommendation. The motivation is, this, with the increase of this enormous number of web services, the demand of personalized service recommendation is increasing, and that is why, to fulfill this market need for service recommendation and to enhance the growth of e-commerce industry, we need a suitable recommendation framework for the services for a particular user. Now, quality of service is one of the primary criteria for service recommendation, and therefore, the focus of today's talk is to introduce this QoS aware service recommendation. So, before going to the details of this QoS aware service recommendation, let us introduce a few things, like the definition of this service. Uh, the service is usually this reusable software component that actually perform a specific task with the objective of this machine to machine interaction for bridging the gap of between business and IT services. So the services which we are going to consider here mainly web services, but it could be, you can think of this different microservices actually. So for example, one automated car is going, it needs to detect what is in front of it, and that is why it needs object detection algorithm. So you can think of this object detection algorithm is a particular service which it needs, and different service provider actually providing different object detection algorithms. So basically it's a logical representation of a reusable business activity having a specified outcome. So if you need weather data, then also you are invoking services, consolidated drilling report, then also we are invoking the services. So here actually for this particular research, we are actually thinking this service in an abstract manner. So we need a set of functional parameters, that's the input and outputs of the services. What are the inputs the service can accept, what are the outputs it's generate, and the set of non-functional parameter deciding its performance. Okay, so this quality of service actually concerns the set of parameters that are responsible for measuring the performance of the services. So these are the few examples of this quality of service parameters. For example, this response time. Response time is the time duration when you are actually submitting a request until you get the response. This time duration will give you this response time. Throughput is the number of clients a service can handle per unit time. Availability, it measured in percentage, how many times the service is available. And reliability, all of we know what is reliability of the services depending on what kind of services we are using, how much accurate results it is giving. Depending on that, this the nature of this QoS parameter actually depends. Again, all these QoS parameters, they do not have the same nature. For example, response time, it's an QoS parameter which we need to minimize. So lesser be the response time, and the service will be more appreciable. Similarly, for throughput, availability, and reliability, our objective would be maximizing all those parameters. So the service having better throughput, better availability, better reliability will be better for the user preference. So there are various domain actually that are associated with this various uh, part of the service life cycle in the services computing paradigm. For example, this web service discovery, it actually, when a user specifies actually what requirements it needs, and depending on that there will be a service discovery algorithm that actually figure out which service could meet the mostly meet the criteria of the user. Then we have the service ranking. Service ranking, it could be based on the functional parameter, it could be based on the non-functional parameter. We are going to rank the services how appropriately it meets the criteria it requires to be satisfied. Then this web service recommendation, which is mostly the focus of today's talk. When we have a set of functionally equivalent services, how we are going to pick up one service that is as per the preference of the user. Sometimes, this single service cannot fulfill the user's requirement, and that is why we need to put multiple services together to fulfill the functionality and produce desired outcome, and that is the research direction which is called web service composition. And when we have this web service composition, how actually we are going to execute these services, in what actions we have to take to proper execution, that is the research area for web service execution. And finally, whatever we are actually looking for and what we are getting, whether they are meeting appropriately, that is the purpose of this web service verification. And as I mentioned, so basically, web service recommendation, this is defined as this: given a set of functionally equivalent services and one or to select a service that is best suited for a given task while satisfying this criteria C. Now, as the title said that this is QS service recommendation, so here our objective is to optimize this QS parameters. So based on the QS parameter optimization, we need to select appropriate service. Now, for service recommendation, actually, what happens in case of this, when the service is getting deployed, the service provider in general uh, gives certain guarantees on the quality of service parameters. There are various way to provide this guarantees. Sometimes they can give that the service can have at max this much response time. So this is the worst case parameter which they can give, but that is not the ideal way to provide this guarantee, because the worst case only satisfying only a very low fraction of time. So relying on the average case is also not appropriate if the standard deviation is very high, and also we cannot service providers probably cannot give the best possible quality of service value which achieve very infrequently for a particular service. So even though the service provider provides this guarantee in terms of their average value of this particular parameter, in reality what we observe that this quality of service parameter, they are not fixed parameters and they fluctuate depending on various reasons. For example, this network loads, unreliable communication, the number of simultaneous invocations on which the service providers do not really have any control over. And this quality of service parameter, they actually fluctuate across different users, different locations, different time steps, and the execution platform where they're actually getting executed. So let us understand with this example actually. So this is the curve, response time curve which we have got for this Make My Trip, Booking.com, Clear Trip, and Expedia. When we tried to explore their hotel services, and we have seen that their response time actually they are changing at different point of time. So basically, when actually we are considering this quality of service as one of the particular parameter for service recommendation, let us understand this is not only the in terms of this time or throughput, it could be the cost as well, or it could be the number of features they are providing as well. Depending on the feedback also, we can actually decide which service works better. So for example, if we think about this microservices level, for example, whatever example I gave, this object detection algorithm, there are multiple service providers who are providing the same service, and which one we have to pick up. This automated service, this automated car requires to detect this object in real time. So we need it to be in fraction of let's say microsecond. If it is more than microsecond, then what will happen? The car may experience this accident, and that is not acceptable. And that is why what we need to do actually while picking up or while choosing this service, we have to be very careful what service we are going to choose. On the other hand, giving you this example in the context which you will probably understand, you probably heard about the name this trivago.com. So what it does actually, it looks at different hotel booking websites, and depending on the user's criteria, it can guide you to pick up the appropriate service. Similarly, if you look at the skyscanner.com, it actually does the similar thing in terms of this flight finding services. Okay, so depending on what is your criteria, whether cheapest flight or fastest flight, you will get all possible set of options. uh, so here the objective is this finding out what could be the appropriate QoS for a particular user, and then pick up the suitable service for that particular user. And as we can see that QoS parameter actually varies across different users, as the second image depicted that if we actually change this user depending on their location or their timing, actually this response time actually vary. The third figure actually corresponding to for a same user and same service, it actually fluctuate over time. So this is the temporal dependency of the QoS parameter. So what we can actually conclude that QoS prediction is an integral part of the service recommendation. So if we can actually predict what would be the QoS value for a particular user for a particular service, then probably uh, we can recommend a suitable service to a suitable user. Now, formally defining this QoS prediction, what we have a set of users, U1 to UN, n number of users, we have this m number of services, and a specific QoS parameter which will be trying to predict. And then we will have this interaction log matrix, which is called also QoS invocation log matrix. So, this is in general this two-dimensional matrix where you on across this row you will have a set of users, across the column you will have a set of services, and when a user has invoked a service in the past, then you can record the QoS information in the matrix. And if the user did not invoke the service in the past, you don't need to um, have the value in the QoS invocation log matrix. So basically it's a sparse matrix, because for a user it's very difficult to invoke all possible services. It can only invoke a small number of services, so very sparse in nature. Sometimes this QoS invocation log, we can have this instead of two-dimensional, we can have three-dimensional matrix, which also we refer to as tensor, where the third dimension is the temporal dimension. And what is the objective? The objective is to predict the QoS value for a given target user service pair. And if it is a temporal QoS prediction, then predict the QoS value for a given target user service pair at a particular time step. So if we look at this QoS our service recommendation, we mainly divide it into two part. On one side, we have this service recommendation without QoS prediction. So even though that is QoS our service prediction, but we are not really looking at what would be the QoS value. Another side, we will be looking at the service recommendation with QoS prediction, which kind of the focus of this today's work. So this QoS prediction problem, if we see the various modeling of this QoS prediction problem, this QoS values, they change across different users. So across users QoS prediction problem, temporal QoS prediction problem, context aware QoS prediction problem, trust aware QoS prediction problem. So these are some of the examples of this QoS prediction problem. So let us understand one by one. So this is the most generic QoS prediction problem, when the primary assumption is this QoS value of a service varies across different users. So this is the QoS invocation log matrix we are talking about. In this across this row, we will have this set of user U1, U2, U3, U4, U5, U6, and across this column we'll have this set of services S1, S2, S3, S4, S5, S6, S7. Now you see this gray column, they are actually we assume they are filled up. That means this user U3 actually invoked the service S1, and that is why we actually recorded the corresponding QS value for that user service pair. So if it is a response time, then we will record the response time value. If it is a reliability or availability, then we will be recording the reliability or availability value for that particular service. Now, as we mentioned that this QS matrix, this QS invocation matrix, this is not a very dense matrix, it's a very sparse matrix. So the idea is for this U3, probably it has actually executed this S1 and S4, but since it doesn't have any idea about S2, S3, S5, S6, S7, so probably when it tries to predict which service would be best for it, then probably you can actually predict what would be the QS value over here, and accordingly you can suggest the user what would be the suitable service for the user. Now, this is the temporal QS prediction problem. Now, on one direction we have this users, another direction we have the services, and in the third direction we have this time step. So, as you see, for a particular user service, let's say U1 and S1, we have this a set of series of quality of service value depending of at what time point the user invoked the service. Okay, so here the objective is to predict QS value for a service for a given target user at a given time step. So this is called this temporal QS prediction problem. Now, coming back to this context-aware QS prediction problem, so this requires additional information of this users and services. So the contextual information of user service helps to improve the prediction accuracy. So it could be the geographical location information or network related information. It could be network location information as well. Other than that, we can have other information, for example, service provider of a service. So there are few examples of this contextual information for user in general: the ID of the user, IP address, the country, IP number, autonomous system, latitude, longitude, the region. These could be the contextual information for the user. Similarly, for the service, the ID, WSDL address, service provider, IP address, country, IP number, autonomous system, latitude, longitude, all this could be the contextual information for the service. Now, the objective over here, given this contextual information, what would be the predicted QS value of a service given a target user? Now, the fourth category for this QS prediction problem is this trust tower QS prediction, where data credibility is a concern. In this figure, actually, we have captured the QS invocation pattern for 6 users, and as you can see that for user 1, 2, 3, 4, the pattern is kind of same. However, if you look at the pattern of user 5 and user 6, you will see the pattern of invocation, service invocation pattern of user 5 and user 6 are different from user 1, 2, 3, 4. Even they are different from each other. So these are the services which are called this gray shift services. Elaborately, we will discuss about this gray shift services. So basically, uh, when a user has this unique pattern of its own invocation and it does not match with the majority of users invocation pattern, then what will happen? We cannot rely on this particular user's data to predict other user or service. So these are the categories of users and services. They probably have very minor help while predicting the QS value of other user services. That is why to analyze the trustworthiness of different user service is very important to enhance the prediction accuracy. So this is trust error QS prediction. Uh, so now coming back to the various solutions for QS prediction, we have for any kind of recommendation, these are two very popular approach. One is this collaborative filtering, another is the content based filtering. Okay, so in collaborative filtering is one of the very popular uh, method for this QS prediction. And now this collaborative filtering also we can actually divide it into this three broad categories. One is this memory based collaborative filtering, model based collaborative filtering, and hybrid collaborative filtering. So memory based collaborative filtering basically depends on the similarity between users and services. In a bit we will actually elaborate what do I mean by memory based collaborative filtering. And this collaborative filtering could be user based, where we are measuring the user similarity. It could be service based, where we are measuring service similarity, or sometimes we can combine the user similarity and service similarity to come up with the QS value for unknown user service pair. It doesn't involve any learning as such. So it's just for the computation of this different metric to come up with the value of this QS parameter. Now, coming back to this model based collaborative filtering, it involves this learning. So, under this, we have this matrix factorization. So, matrix factorization, either we can do this singular value decomposition, or we can do this non negative matrix factorization using different machine learning or deep learning technique. Then we can have this factorization machine and various deep learning architecture. Sometimes we can combine this memory based and model based approach and come up with this hybrid collaborative filtering. So let us discuss all this approach in a very brief manner. So this is what we want to say, this memory based collaborative filtering. So it leverages similarity between users and services. So if you look at this figure A actually, so given this matrix, what we need to do, we need to predict the value of this user UI and service SJ. What we can do actually, this is actually this user based collaborative filtering, where we are looking at various users data for a particular service, and we are taking, either we can take the simple average to predict this value, or we can take this weighted average, where the weight could be the similarity between this user. So for example, uh, we are going to take the average of this u1 to un, all the users um, QS value for the service SJ, and then we can take the similarity as the weight, similarity between UI and every other users. So when we will be considering U1, then what we will do, we will take the QS value of this and multiply it with the similarity value of U1 UI. For U2, we are going to take this value and multiply it with similarity of U2 UI. So this is the weighted average. Similarly, for service also we can take this row average, where we have all the services value, services QS value, we can combine and we can find out what would be the QS value over here. So the hybrid method is combining this user based memory based collaborative filtering and service based memory based collaborative filtering. We can either use this linear combination or leveraging this deviation based method, or we can use the various learning based method for the purpose of aggregation. Now, for computing the similarity, we can use this cosine similarity measure, Pearson correlation coefficient, the ratio-based similarity, Jacob similarity, Haversine distance. These are a few popular similarity function which we use for memory-based collaborative filtering method to compute the similarity between users and services. So, as you probably know, this is the cosine similarity measure between these two vectors vi and vj, and then we have this Pearson correlation coefficient. These two, I think, all of you are very familiar with. The next is the Haversine distance function. So instead of this between the QS interactions, the similarity between the QS interactions between two users, what we can do, we can actually figure out the geographical similarity between the users. So it actually takes this latitude and longitude information and find out this Eversign distance, and accordingly we can say that these users are kind of similar because they are co-located, or whether they are dissimilar because they are actually residing in across different location across this globe. Now, this Jacob similarity is actually telling if the similarity between two services, let's say we are computing, then how many users actually commonly access these two services, and in total, what would be the number of users that actually individually um, invoke service SI and SJ. Ratio based similarity measure actually the summation of the ratio between this minimum value and maximum value across all the values of this particular vi could be either user or service. So if vi is user, then we will be considering that what could be the qik value. Okay, so when ith user invoked kth service, what would be the minimum value between I and jth user, and what is the minimum value between ith j user over this kth service. So this is how this ratio based similarity is computed, and finally we can use them as the weight parameter to compute this memory based collaborative filtering. uh, the main advantage of having this memory based collaborative filtering, they are very simple, and of course they are explainable mm, in nature. So this actually very advantageous in the era of explainable AI. We can actually explain why we are recommending these services. On the other hand, there are multiple disadvantages. First is the high sparsity of the matrix. And since the matrix is very sparse, so while computing the similarity between two rows or two columns, we may not have sufficient data to compute the similarity. So high sparsity is one of the reasons because of which we are not getting very high accuracy using memory based collaborative filtering. The other disadvantage could be inability to capture non-linear relationship among QS data. The presence of outliers. So if there is one outlier in one of the rows or one of the columns, then the average value will be sensitive to that particular outlier. And of course, the presence of gray shift users and services, since they have very unique pattern of QS invocation. So it's very difficult from their pattern to predict what would be the value of the QS parameter for a normal or regular user service. There is a problem with this cold start problem when a new user or new service added into the system, since they do not have any QS data a priori, so we cannot actually calculate the similarity. And that is why for this memory based collaborative filtering cannot explicitly solve this cold start problem. Low scalability issue because of the high dimensional data, because while calculating this, let's say, Pearson correlation coefficient or this cosine similarity, if the number of users and number of services are very high, then mm, calculating this cosine similarity, let's say we have this n number of users and we need to compare this pairwise cosine similarity, then we have to compute nc2 number of calculations. So it's a huge computation, and if the QS vector is high dimensional, then it is again computationally very expensive. So scalability is definitely a problem with this memory based collaborative filtering. And then there is a high responsiveness due to the handle of this high dimensional data, and that is why memory based collaborative filtering is not suitable for real time system. And then what people thought of moving this memory based collaborative filtering to overcome some of the limitation and tries to move to this model based collaborative filtering. The first thing what they have done to try to solve this scalability issue using different clusters. So these clusters are being calculated offline mode. So similar users and similar services are put together in a same cluster, and then These clusters are generated, it could be based on this QS data or contextual features or derived features. Once this clusters is computed, then within that clusters, memory based collaborative filtering methods actually applied. So since the cluster will have only a few number of users and services, so the complexity will not be that much high while handling the entire set of users and services. So in a sense, this will be scalable. uh, Now this there are many limitation, many other limitations because of which we are not getting this appropriate or desired prediction value. And that is why, to solve some of this difficulty, for example the scalability, sparsity, cold start problem, and capturing this nonlinear relationship QS data, we need to explore this model based collaborative filtering, which includes this matrix factorization, machine deep architecture, etc. So this is the matrix factorization. So when we have this partially filled up QS invocation log matrix, then what we can do, actually we can decompose it into low rank two matrices, and while combining them and reconstruct the original matrix, in this process we can actually come up with the values of this cells where we don't have any valid data. So this is the idea of matrix factorization. Of course you can go and do this singular value decomposition, but what we prefer usually here is this non-negative matrix factorization, where actually what we do actually, uh, we divide this user and service, this latent space. So let's say we have this d-dimensional features of this users and services, and when we combine this u and s transpose, these two matrix, then we will get the we can reconstruct this overall matrix. And once we reconstruct this overall matrix, then we can compute this loss. This loss is the original value and the value which we deconstructed. After deconstruction, whatever value we will be getting, that value. So this is the predicted value, difference between original value and the predicted value, and we take this squared. So this ij, this is the indicator variable. It is telling us whether we have the original value of this qij or not. So whether if we reconstruct this value, we cannot find out loss for this particular cell, since we do not have the original data. However, we can have the original data at this location, this location, this location, this location. So in all this location which are filled up in the original matrix, for them actually we can calculate this loss, and our objective is to minimize this loss. So this is how we can actually calculate this loss function. And then to avoid this overfitting issue, we can use some of the regularization method. So this is very popular regularization method, L2 norm. Okay, we can actually use to restrict this overfitting problem. So this is non-negative matrix factorization we are talking about. There are a lot of work that have been done to explore this matrix factorization. And also in the additionally in matrix factorization, they come up with some of the improvisation um, to solve some of the limitations of this matrix factorization. And additionally, some of the papers actually utilize some of the contextual information also to mm, to improve the accuracy for this matrix factorization method. The advantage of this matrix factorization, this is scalable and resolve this data sparsity and cold start problem. However, it requires this few hyperparameters to tune. For example, if we need to figure out d-dimensional latent space, then what would be the value of d? And then need additional reconstruction when new user and services is needed. So once we have this n number of users and n number of services, we can do this matrix factorization again when a new service is added, making the number of services equal to n plus 1. Then we again need to do this reconstruction with the I mean from the scratch. And also it has another problem that it is unable to capture this nonlinear or complex feature hidden in the QoS data. And that is why, even though we can solve some of the problem with this memory based collaborative filtering, we cannot solve all the problem to achieve the desired QoS prediction accuracy. And that is why people have looked at this factorization machine approach, where instead of this user and service interaction, what essentially we will emphasize on a particular user service interaction. So this is the user interaction QI and all possible QJ interaction. So it actually figuring out the second order feature. So matrix factorization, while captures only the linear feature, it can capture the second order features. But that is all the advantage it has. So if the relationship among this QoS data is more complex, so it cannot actually identify this issue. And that is why people try to explore this deep learning based QoS prediction approach. They try to use this simple multi-layer perceptron or autoencoder to establish the relationship between users and services. They can actually leverage this contextual data of users and contextual data of service, put them together and pass it to a MLP network to predict what would be the value of the QoS given that the contextual information of these users and services. So there are few approaches which have used this contextual data and come up with their QoS prediction mechanism. So some of them have used this MLP for this learning. Um some of them have used this contextual data, for example, geographical location, network location, the ID, the country information, latitude, longitude, all this information they can actually combine and pass it to a network to obtain this the prediction between this uh, users and services. Okay, the QoS value of user services. So the advantage of deep learning based architecture, it actually enables the model hidden complex feature and comparatively very high accuracy. But the computation time, if it is a online learning, the computation time is very high, and contextual information may not always be available to explore the entire space actually. Sometimes we can use this hybrid information, that is memory based and model based collaborative filtering, combine them and come up with the hybrid collaborative filtering for QoS prediction. So there are few papers that have actually worked on this hybrid prediction. For example, in the CAHP this paper, actually what they have done, actually they first use this memory based collaborative filtering for the data imputation purpose. And once they filled up this matrix, then they extract the feature values of this users and service from their raw QoS values, and then they come up with the neural network framework to predict the QoS value of a given target user service pair. So these are comparatively very high accuracy, but with the compromisation on the computation time also. So they have a very high response time, and that is why they are not suitable for real time purpose. For trust our QoS prediction, the main problem is very few literature actually have worked on this trust our QoS prediction. And the one of the prominent problem in this trust our QoS prediction is to define the trust. How people actually define what should be the mathematical notion to define this trust. So some of them, what they have done, actually they have clustered these users and services, let's say using k-means clustering, and the clusters having very few number of users, or let's say the number of users, if that is less than a threshold, then they can say that these particular users, they are untrustworthy user. So they can actually remove all those users and then predict for the user service pair for the rest of the users. So there are a few methods only. They have actually have done this thing, trust aware QS prediction, but the problem is this no standardized this notion of this trust. Uh, mm, Coming back to this temporal QS prediction, which is also known as time aware QS prediction, people have used this LSTM or GRU unit for predicting the QS value of a given target user service pair. So the spatio-temporal feature information actually, while using this LSTM, probably people have invested. Sorry, you have any question? Hello. Okay, let's continue. So, while investigating this LSTM and GRU, even though people have tried to capture this temporal dependency among the data, but they often fail to explore the spatio-temporal relationship among the QS data. So this is very important aspect when we are actually, while designing this QS prediction framework, the challenges which we need to actually concentrate on. This is the QS prediction problem. The objective of this QS prediction framework should be having very high accuracy, very low response, less high responsiveness in terms of very low prediction time and high scalability. So, while achieving this high accuracy, there are certain challenges which we need to address. One is, of course, the data sparsity, because the QS invocation log has very few data. And then this cold start problem, when a user or service added to the system, they do not have any past user service interaction. Non-linear or higher order complex relationship among QS data, influence of uncorrelated user service, presence of uncorrelated user service interaction, complexity of QS prediction, complexity of QS prediction framework,
Hello, 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 hello. Ma'am, you are not audible. Hello, are you there? Are you there, ma'am? Hello.
Hello.
Now you are audible, ma'am.
Okay. So you can see my screen also?
Yes, yes, we can see yours.
Okay. So, did you listen this QS prediction challenges?
Yes, yes.
Okay.
Hmm.
So, considering all these challenges, what we propose is anomaly resilient real-time QS prediction framework using graph convolution.
Okay.
So let us first understand this graph convolution and how exactly it works. So we know this convolution neural network, right? It actually works on the images, where actually we can extract the spatial information from one image, and we can use those information for the classification or regression problem. Now you see, even though we have a matrix over here, the QS prediction matrix. So let me just
Huh.
draw here. So even though I have this, let's say I have three users, U1, U2, U3, and let's say I have four services, S1, S2, S3, S4.
Okay.
Okay.
Hmm.
Now what will happen if we try to extract, if we try to look at this particular region and try to use this convolution operator, will it work? So that is the main question, because when we are actually using this image, relationship between two adjacent pixels. But when we are using this QS invocation log matrix, what is the relation between this Q of U1 S1 and the very adjacent of this Q of U1 S2? Because this S1 S2, these two services could be very different in nature. So maybe from the data of S2 we cannot actually predict S1, so it is completely unrealistic if we use this convolution operation over here. And that is why for this recommendation we come up with this graph convolution, where actually we need to define this graph between the interaction. So the graph, the first, when we are representing this framework in terms of a graph, so we need to define the nodes and edges. So the nodes, so this is a bipartite graph. This is the interaction graph between users and services. So on one side we have the set of nodes corresponding to each users. Another side we have a set of nodes corresponding to each service. Now, what will happen if one user has invoked one service, then we will have one particular edge. So, if there exists one edge between this UE1 and SE1, that means that user 1 has invoked this service 1. Okay. So, this is how this is the interaction graph. This is how this graph has been generated. So, this is called this QoS invocation graph. Now, once this graph is generated, the next question is, how do you actually represent this graph? So, in order to do this convolution operation, we represent this graphs in terms of this adjacency matrix. So, as the adjacency matrix, as per the definition of the adjacency matrix, we need all the nodes of this graph um, as a matrix dimension would be in capital N cross capital N, where capital N equals to small n plus small m. Yeah, you have any question?
No, 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 ma'am. Carry on.
So small n represents this number of users and small m represents this number of services. So you will have this entire interaction matrix. So for this case, actually, so if we have this interaction between, let's say, u1 u2 u3, and we have this s1 s2 s3 s4, and let's say we have this interaction between u1 u3 and s1, we have only interaction between this and we have interaction between these two, then here in the sorry, yeah, so u1 u2 u3 S1, S2, S3, S4. So these are the nodes of the graph. And additionally, we have this U1, U2, U3, S1, S2, S3, S4. And what we'll do, if there is one edge, then we will have one. So we will have 2, 1, and rest of the part we will have 0. So this is the adjacency matrix.
Ma'am,
So similarly,
ma'am, the matrix dimension will be uh, 7 cross 7.
yes. So this is n cross n, where n equals to this
M
capital
plus
N
n.
equals to
M plus
small
n.
n, yeah, small n plus m. So
Okay.
this is number of users plus number of services. Okay.
Okay. Uh-huh.
So
Got it.
this is how this adjacency matrix is computed. Now you see this adjacency matrix, when we are looking at the degree of this matrix. Now, if one particular user has multiple invocation, this user has higher invocation. Let's say you have this 100 services and this particular user invokes 60 services. On the other hand, this particular user does not invoke too many services, it has only invoked 2 services. So the degree actually depends on the number of invocation, and that is why to reduce the influence of this degree, we actually normalize this adjacency matrix in this manner. Okay, so this is the vectorized operation. This D stands for the diagonal degree matrix. So the diagonal degree matrix means it's a diagonal matrix, only we will have this diagonal elements.
Okay.
So in this example, so if we have this matrix, So only this principal, along this principal diagonal, we have this element, and this will be the degree of u1. So the degree of u1 2, so this value will be 2. The degree of u2 is 1, so this value will be 1. So and so on. The degree of this is 3, this is 1, this is 1, this is 2, this is 1. Okay, so this is the degree matrix. And since some of them could have high degree and some of them could have low degree, and that could influence actually the calculation, and that is why we normalize it. How do I normalize it? So this is the actually vectorized operation. If you look at the corresponding scalarized operation, we actually divide every entry by the degree value corresponding to dii and djj. So if aij is one entry, then we are dividing it square root of dii and djj. So it will normalize these values. And now it does not depends on the degree, it only depends on the interaction. Okay.
Yes.
Now, for this graph, what we can actually do, we can actually figure out for each of this node, we actually figure out the embedding for this node. Embedding will be the initial feature vector for the users and services. Okay. Once we have these users and service, we will see what is the advantage of representing this recommendation problem in terms of this graph convolution. So these are the features actually we used for this graph convolution neural network actually. So as we pointed out, this there are various kind of information could be available. So what we have done, we have extracted QoS information. Also, we have extracted contextual information. From the QoS information, what we have done, so you see, we have this QoS matrix. So we have this U1, U2, U3. These are the users, and S1, S2, S3, S4. These are my services. And now here, this is actually the QoS invocation vector for this user UI. This is the vector. Some of the values are invalid because the user UI, if it does not invoke some of the services, so some of the value could be invalid. Some of the values are valid. Okay. So from that, what we are going to do first, for every users, we are going to calculate statistical information. Statistical information includes this minimum value, maximum value, the average value, standard deviation, and the median value. Okay, so these 5 statistical information actually we used here. And then what we did, actually we used the next thing is the similarity based features. Similarity based features means if we have n number of features, then we are actually calculating for each user what is the similarity between every other user. So for this u1, we will have the similarity between u1 u2, also u1 u1 u3. So these are two similarity values. So if we have this n number of users, then we will, for each user ui, we will have n minus 1 similarity values. So similarity value will be similarity between ui and uj, where this j actually varies from this 1 to n but not equals to I. So that is why this n minus 1 value. So these are the similarity values which actually we used for another set of features. And then we use this QoS based feature, which we obtain using this non-negative matrix factorization. So we decompose this matrix into two part and then try to combine it, how it is actually giving you the latent features for these users and services. And similarly, we used a few contextual information. For example, contextual information from autonomous system, country, and also the geographical location. So one is from the network information, another is from the geographical distance. Okay, so for in order to calculate geographical distance, we use the Sieverts distance function. And if the number of users or number of services will be very high, then this particular value, this similarity value computation or QoS based feature, these values will be very high. And that is why we use this autoencoder to ensure the scalability. So if my original feature is n minus 1, then we come up with this latent feature of dimension, this ds. So the overall feature dimension is 5 plus ds plus dq plus dc plus dg, where 5 is the 5 statistical features: mean, max, median, average and standard deviation. Then ds is the number of similarity features. To obtain the similarity features, we use this autoencoder to reduce the dimension from n minus 1 to ds. So ds is a hyperparameter. We can choose any value of it depending on the architecture of your machine where you are going to execute your program. And dq is the non-negative matrix factorization. So what would be the latent space? Depending on that, actually you can have this dq. dc is the contextual information, that is this AS, one had encoding for AS country of UI, and then applied uh, this autoencoder to come up with this latent feature space. And finally this geographical distance based feature vector. From that also we can apply this autoencoder to come up with this entire feature vector. So these features actually will represent the node features. So each individual user and service, they are actually represented by this node feature. Is that okay? You have any
Yes,
question?
yes, ma'am. Actually, ma'am, please make your slide full screen.
Yeah, I have done that.
Okay, okay, sir. Okay, ma'am.
Okay.
Hmm.
So now coming back to this convolution operation, how actually it works. So this is the function for this convolution operation. So this is the adjacency matrix, normalized adjacency matrix. This is the feature vector, and this is the weights and bias. These are the learning parameters. So basically what is happening, you see the adjacency matrix is of n cross n dimensional. Now this feature matrix, this will be n cross f dimensional. So n is the number of users and services, and f is the total dimension of this encoding, which we obtain from this figure f equals to 5 plus ds plus dq plus dc plus dg. That will give you this entire feature vector f. Okay.
Okay.
Then if you multiply a cross f, then what essentially you are getting, this is very important to understand. So basically what is happening here, actually, if you are taking this particular row, okay, and then you have these features, okay.
Hmm.
So this is the what you are going to do. You are going to multiply this row with all this column and sum it up to get the individual value for this one. Okay.
Yes, yes,
So you see here, actually some of the values are 0 where you do not have any connection, and some of the values are 1 where you have this connection.
yes.
So if you multiply them, actually, so what will happen? Those for which you do not have this connection, these will be discarded.
Good. Yes.
Only this part of this matrix will be, you are going to take, you are going to consider only this part of this matrix. So this part means what? These are the part, that means these are the direct neighbor of yours. So basically using this convolution operation, what you are doing, actually, you are combining your one hop neighbor information. So if if we are doing this convolution operation one step, then what we are doing, we are combining the information, the embedding for user to its immediate hop. That means immediate hop means s1 and s3. It is user 1 is connected with s1 and s3. So the embedding for s1 and s3 will be combined with the embedding of u1 to come up with the spatial information, to extract the spatial feature for this u1. Is that okay with you?
Yes, yes.
Now the point to be noted here, actually, when we actually do this thing, you see we also add the identity matrix here. So the purpose of this identity matrix, while combining this feature, not only we are going to combine the feature of this one, we also going to combine the self feature as well. So if you see in the adjacency matrix across diagonal, so u1 there should be the value of 0 because there is no self
Yes.
loop, and
Hmm.
that is why the value is 0. But
Yes.
here, while doing the convolution operation, we need to make sure the feature of itself will be combined its self features, and that's why we have added this value, so this identity matrix. So that is the purpose of this identity matrix. Is that okay with you?
Eh, yes, yes, ma'am.
Okay. So now this convolution operation, what it does actually, first it is doing this linear operation, which is the simple matrix factorization. Then it what it does, it is combining this ReLU function, which is a nonlinear function, with this weight and bias, and then it is actually going to give you this value, combined value. Now what we can actually see from this, why this graph convolution operation is very effective in this context. First of all, it handles data sparsity. How it is handling data sparsity? Because while considering this one of features, it is only considering those features which is connected to that particular user. So I want to combine this user's feature with the set of services feature which it has already interacted. So it is only going to combine this user feature with the service feature of s1 and s3. It is not going to consider the features of s2 and s4. So that is how it is handling sparsity. Even though you do not have the interaction, it is not going to compute it. So it can only handles, it can only compute whatever information you have. So it is actually handling the data sparsity. Second thing is, it is also capturing the non-linearity, because here you see we have used this ReLU function which actually captured this non-linearity, and that is why we have introduced the non-linearity. Also, here what we are doing actually, we are extracting the spatial information, not only the users or service individual information, but we are capturing the global information, the interacted information of the users and services. Is that okay with you? Have
Okay.
you understood the effectiveness of graph convolution?
Yes.
Okay. Now, what we did with this graph convolution, we designed this multi-layer, multi-head graph convolution matrix factorization. Now, see, why this multi-layer and multi-head graph convolution matrix factorization we are talking about? These are the multiple head. Okay, each
Yes.
head is this. So it stands for graph convolution matrix factorization unit. Okay, so
Yes.
it combines this linear information along with this non-linear. Okay,
Okay.
now what we it's a very analogous to the traditional convolution neural network where we use multiple filters. The purpose of this filters is to capture a specific features, right? So some of the filter, in case of image, one filter actually acts as the edge detector. Another filter, what it does, it can blur the image. Another filter, it can sharpen the image. So different filters has different purpose, different ways to capturing different features. So similarly here also we use different graph convolution matrix factorization unit to capture different features, and that is why this multi-head comes into the picture. Once we do this multi-head operation, then what will happen? So we started with the initial feature vector n cross f0, where n is the number of users and number of services, addition of number of users and services, and f0 is the initial feature vector. We started with this. Once we apply all this, then what will happen? Additionally, we will have this third dimension, which is the number of heads. Now, what we need to do actually, we combine them using one cross one convolution. So, what one cross one convolution does, it actually combine them channel wise. So, after this one cross one convolution, we will have the dimension n cross f0 again. So, this is the part of this multi-head convolution where we apply multiple head and combining them to capture different features. Is that okay?
Okay.
Now, the notion of this multi-layer, you see, this is the multi-head graph convolution.
Yes.
MHGCMFU, this is the multi-head graph convolution matrix factorization unit, which we actually execute it into multiple times, t times. So, what is the purpose of this multi-layer graph convolution? So when we apply the first level of graph convolution, then what we actually capture, we capture the next half information. Okay.
Yes.
So when again second time we are applying this convolution operation on top of the derived feature. So derived feature means what? So if we go back to our examples, so after one level of convolution, what happens? The user u1 feature, it says it's now the function of u1's feature, s1's feature, and s3's feature. Okay.
Yes.
And what is s1's feature is the function of it is s1 its own feature, u1's feature, and okay, no one else. And what is this s3? S3 is the function of e1,
Yes.
s3, and u3. Okay. Now, in the second level of convolution, it will be the again function of this user, this service, and this S3. Now, this user is the function of U1, S1, S3. This service is the function of S1, U1, and this service is the function of U1, S3, U3.
Yes.
So, while combining these three, actually, what we combine? We combine the feature of U1, S3, S1, S3, also U3. So what is the relation between U1 and U3? It's the two hop relationship. It's not the direct relationship.
No.
So you see the path length is 2. So all the features we are combining where the length is 2.
Okay. You want to say? Okay.
Is that okay or should I
Yes.
repeat?
No, no, yes, yes. To reach from U1 to U3, that is two hop path. It
Yeah.
is from
So
U1 to S3, then S3 to U3.
yeah, you want to S3. So in the first level of when we applied first time this convolution operation, then
Yes.
basically what we did, we combined U1's feature with S3's feature.
S3 features.
Now the embedding contains this U1 features, S3's feature, and
Yes.
S3 contains the feature of U1, U3, and S3.
S3, huh?
When second time we are combining S3's feature, S3's feature now consists of U3's feature. So
Yes.
second time when we are combining U1's feature, it consists of U3's feature also.
Also, yes. Yes, yes.
So the time we are repeating this convolution operation, that means what we are doing essentially, we are taking multiple hops relationship. Okay, so this is the purpose of this multi-layer. So multi-layer explore this multiple hop spatial relationship, and multi-head is actually extracting different characteristics of the feature. So this is what we actually proposed. And then what we did actually, we did this channel wise concatenation. So in the first time we are getting the first of feature, second time we'll be getting the second of feature, third time we'll be getting the third of feature. So there is a problem with this graph convolution which is called over smoothing problem. Okay, over smoothing problem means if you apply this multiple graph convolution operation, then what will happen, the individual characteristics you are actually will lose these characteristics because you try to combine more and more characteristics. So while combining more characteristics, you are losing the individual characteristics. So data morphing problem will come. Okay, and
Okay.
that is why what we did here, using this channel concatenation, we use this residual or skip connection featured over here. So this is the residual connection we used for channel wise concatenation followed by this convolution. So if some information is lost due to the multiple this convolution operation, we can actually extract those things using this residual information. So that is the rationale behind this channel wise concatenation followed by this convolution. And then what we have done actually, we decompose this into two sets of f0. Okay, so these will be the user embedding, spatial extracted user embedding. So initially we started with the initial embedding, now we actually incorporate the spatial information. So this is auto extracted feature. Auto extracted feature is the function of its own feature and also the spatial features. So these auto extracted features, now if we actually combine using this multiplication, so this is actually doing matrix factorization. That is why I elaborated matrix factorization method before that. But we did not use this vanilla matrix factorization. We use this graph convolution matrix factorization to include the spatial information of the users and services. Is that okay? Any questions so far?
No, no. Actually, one doubt is there. By using multi-layer and multi-head graph convolution matrix factorization, what we are doing, we are improving the quality of service.
Not really. What is our objective? Our objective is to quality of service prediction. Okay.
Yes, yes,
Now that is why we started with these different challenges. Okay. So
yes,
what are
yes,
the challenges we usually encounter by the state of the available state of the art methods?
yes.
We saw that data sparsity, because this QS invocation log is sparse in nature. So data
Yes,
sparsity, one problem. Cold start, another problem. Non-linear relationship, capturing this non-linear relationship, one problem. This uncorrelated user service information, this influence of uncorrelated user service information, that is one problem. Gray shape, one problem, and outlier, one problem.
yes.
So we tried to
Overcome,
address all those problems. So what
overcome
graph,
these problems.
yeah, graph convolution does actually, it actually handles the data sparsity problem and also captures this non-linearity.
Okay.
So it can establish the relationship among various QoS data. Okay, different user service QoS data. This collaborative information also we are extracting, also we are ensuring this capturing this non-linearity.
Yes.
Okay, and the purpose of this multi-head, as I pointed out, extracting different features,
Yes.
and the purpose of multi-layer to incorporate more spatial information from in hop neighbors, or rather T hop neighbors here. Okay.
Okay. Okay. I got it.
Now what we did here actually, in order to calculate the loss function, earlier what we saw, we in general, in normal matrix factorization, what we saw here, people usually use this MAC as the loss function. Okay,
Yes. Yes.
mean squared error. Okay,
Instant.
but what you will see that mean squared error is outlier sensitive. What do you mean by outlier sensitive? If one value is outlier, okay, so outlier means that is far from the all other values.
Yes.
So the error will be very high, and if you actually using that error to upgrade your parameters, then your upgradation will be biased on the basis of the error.
Error. Minimization.
So MAC, the problem with MAC is that it is outlier sensitive, and that is why instead of MAC in our framework we have used this Cauchy loss. So you see, this is the MAC part, Qij minus this is the actual value, this is the predicted value, then we have taken the square. Okay, and this gamma is one hyperparameter. You can set its value manually. Now,
Okay.
since we have done this log, so even if the actual value is very high, due to this log part, what we ensure that the overall error will be very less.
What will be the range of the gamma?
You can take any value. I mean, it's not between 0 to 1. We tried with 0 to 100.
Any integer.
Yeah, any integer or any real number,
Okay.
any positive real number, not
Okay.
only integer. Okay.
Okay. Okay.
So what we have done actually, so basically log 0 is undefined, and that is why we have this quantity 1 plus, because if the actual value and predicted value overlap, so this
Zero.
quantity will be 0.
Zero. Yes.
So that is why 1 plus. And how much you want to reduce this value, that depends on this gamma square. So gamma square is basically a positive quantity, which is I mean, you want to scale it down, and that is the purpose of this gamma.
To scaling
On
it.
Yeah, on top of that you have this log. So if the error is very high due to the outlier, then you can actually reduce this error.
Minimize it. Okay.
Yeah. So this is outlier resilient loss function. So we incorporate this outlier resilient loss function, so it will be robust for the outlier also. So is this architecture clear to you?
Yes, yes,
So what we have done actually, this is our featured extraction block where we have this contextual feature, collaborative feature, statistical feature, and similarity feature. And using this feature, what we did QS invocation graph, and then we use this multi-layer, multi-head graph convolution matrix factorization. Okay,
yes,
but this only solves this sparsity and outlier resilience. Okay, so this is instead of this ARRP, which is the name of our framework, anomaly resilient real-time QS prediction framework, we only solve this sparsity and outlier. So this block, we named it SORRQP, sparsity outlier resilient real-time QS prediction block. So now if we look at the challenges, we see that data sparsity problem we solved, higher order relationship, nonlinear relationship, uncorrelated influence of uncorrelated user service relationship we have taken into account, and presence
yes.
of outliers also we have
Also
taken
taken.
into account using Cauchy laws. But the cold start problem and presence of gray sheep user service problem, that still remains. Why
Yes,
so? Because for cold start problem, a new user, when a new user introduced, there is no connection. So if you look at this graph, when a new user has been introduced, there is no connection between the services because it did not interact with any service. So it will be one isolated node. So if you look at the corresponding row or corresponding column, all the values will be zero. So
yes,
if you want to multiply the feature you will get, it will be
zero.
only its initial feature,
Yes,
not the spatial feature. And that is why the cold start problem will not be addressed by graph convolution. And also it suffers with the presence of gray sheep. So this is one example which we have extracted. There is an example of 4 users and 12 services. Okay, as you can see, the QS invocation pattern of these 3 services are almost similar apart from 1 2 cases. But if you see the QS invocation pattern for this green user, it is completely different. You see,
yes,
so the characteristics for this user is completely different. This is called gray sheep user. So now we need to handle those users. So if we want to predict what would be the QS value from this set of users, can we do it? Of course not, right?
yes.
Because it has a complete different pattern. Unless we capture this particular pattern of the user, we cannot actually predict this. And that is why we introduce 2 additional block in our framework. Okay. So the first block is the gray sheep detection block, where we identify one user gray sheep, then we will handle it separately. Cold start user service, identifying them is pretty much easier. From the QS invocation log itself, you can identify whether it's a cold start user or services. But for gray sheep, what we did actually, we first compute this reliability score. What is this reliability score actually? So basically, what we did actually, so yeah, so this is the information. This is the let's say you have this U1, U2, U3, S1, S2, S3, S4. Now if you look at this service QoS information, so this vector will give you the service QoS information. So from this vector, what you can obtain? You can obtain mu and sigma. Okay. Now, if the sigma is too high, then what you can tell, what you can infer, that from the mu value, from the average value, it actually deviate too much. Okay. But if the sigma is very low, let's say this is my 5 millisecond and this is 0.01 millisecond, then what you can say that in general, the average response time of this service is 5 milliseconds. Even it deviates this much, right? But if it is 5 millisecond is the mu and 6.5 is the sigma, then what you can infer actually, even though my mean is 5 millisecond, but it can deviate too much. It could be 11.5, it could be 0 also. I mean 0 point something also. Okay. So the deviation is very high. So keeping that in mind, what we did actually, we normalize first this standard deviation. Okay. So from all the services standard deviation, what we did, So this is the individual service standard deviation. This is mean value, and this is max minus mean. So these will give you the normalized value for standard deviation. So this is the normal normalization method. Then what we did, this 1 minus this value, okay, this is going to be the reliability score. So if the value is very high, then what do you mean by that? The standard deviation is low, and that is why this value is high. So that means this service is more reliable, right? Standard deviation is low. That means the first case. So this, the reliability of this service is high. The reliability of this service is low. So that is how we figure out this reliability score. Once we figure out this reliability score, then we actually define this gray sheep anomaly score. What is this gray sheep anomaly score? So gray sheep anomaly score is actually individual value Qij. Okay, so we are finding out gray sheep anomaly score for user I. So what is this gray sheep anomaly score? With respect to every value of this UI. So we are changing this J. Okay, all the J that invoked this UI, all the services Sj that invoked by UI, we looking at this individual value, and we subtracted the user mean and also the service mean. Okay, and we take the mode of it. So with respect to this user mean and service mean, how much it deviates, okay, and then we multiplied it with the service reliability score, and then we just average it up. That means what? If the reliability score is very high, also this deviation is very high. That means even though the service is consistent, but user is not consistent on that particular service, so the abnormality of this user will be more. So this is how we calculate this GS score. Okay, gray sheep abnormality score. Based on that, we define this gray sheep users and services. We say that if the GS code actually more than a threshold value, then we will actually identify them as gray sheep users or services. Okay, and this is not just the hyperparameter which we tuned externally. We actually, this is the data driven hyperparameter. We actually find out the threshold value from the data set itself. Okay, so this is the overall ARRQP framework. So this is the feature extraction block, and this is the this is the SORRQP. So sparsity and outlier resilient real-time QS prediction block. So this part we have already discussed. Now we need to discuss these two parts. This is GRRQP, gray sheep resilient real-time QS prediction framework, and cold start resilient real-time QS prediction framework. So let us talk about this gray sheep resilient QS prediction framework. So what we do actually, for every user service for which we want to predict the QS value, we first check whether the user is gray sheep or not. If it is gray sheep, then we will pass it to a separate MLP having the feature of the embedded feature which is extracted from this SORRQP block, okay, which is represented by this capital E, the initial feature and the gray sheep score. Okay, combining all of them, we use this multi-layer perceptron to obtain the QS feature. So it is actually not only along with the normal or regular user service we are predicting, for the gray sheep user service, we are separating them out. We are trying to capture their own characteristics and figure out what would be the QS value. So this block is only giving the embedding. This block is not giving the QS value. Additionally, we apply this gray sheep value, gray sheep scored value, and then we come up with this value. Is that okay?
Yes.
Similarly, for cold start user, see, the statistical information and similarity information is useless for cold start user, right? Because similarity between this user and any other user we cannot figure out because we don't have any information of the current user. Okay, because this is the new user. And statistical information, mean, max, median, average, and standard deviation, we cannot extract because we do not have any data. But the contextual information we will get, and using non-negative matrix factorization, we will get this non-negative matrix factorization feature. So using those two features, if we pass them in a MLP, okay, then we will get the cold start. So in the cold start, for cold start user and service feature, instead of using the personalized or local information, we are using the global information. Okay, global information and local contextual information, combining them together, we try to predict what would be the QS value of a target user service pair when one of them or both of them are cold start. Is that okay with you?
Yes, yes.
So this is the framework which we have designed. Any questions so far?
No, ma'am. You can go ahead.
Okay, if you do not have any question, then let me talk about the experimentation which we have done. So
Yes.
basically, there is a dataset called WS Dream dataset, which is publicly available. It consists of 339 users and 5825 services. What we did actually, so this is the statistical information of this QS. So there are two QS parameter, one is response time, another is throughput, and this is the range of the response time is 0.001 millisecond to millisecond to 19.999 millisecond. And similarly, the throughput value actually varies between 0.004 to 1000, and median, mean, and standard deviation values are given. For user and service, these are the contextual information which are available as part of the dataset. But for not user service, it is available. For some of them, this is available.
Okay.
What we did actually, we did this training testing split up. So if X% training data set of the overall matrix we used, so you see the original matrix which is given, that itself is sparse matrix. Now
Yes.
considering this X% training data set, we make it more sparse. We use them as the training data set. So every user service value, user service pair, we are actually using them for the training sample. Okay,
Okay.
and then remaining 100 minus X%, we are using them for the validation and testing data
Yes,
set.
sir.
The for the comparison metric, we use actually mean absolute error and root mean squared error. These two
RMS.
actually, this yeah, RMSE and MAE, these two metric we used for performance analysis. So while MAE actually captured the overall error, you see the RMSE,
Hmm.
what is the formula of RMSE? You are doing the you are finding the
Mean
error, then you are squaring it up, then sum it up, then take the square root,
square
right?
root. Yes.
So while doing the squared, so that means if the error is high, by squaring it, you are making it large.
Large.
So while MAE, for every error, you are giving equal weight, right? For every error, they have equal weight. For RMSE, this large error will have more weightage because you are doing the square.
Square.
So
Yes.
squared value will be, so if the error is 2, then squared value will be 4. If the
Yes.
error is 3, squared value will be 9. So
Yes.
more the error, you will have more weightage. So that is the purpose of RMSE. With these two metrics, actually, we compared this with a set of other methods. Okay, so we have divided this set of methods with respect to memory-based collaborative filtering, model-based collaborative filtering, and hybrid collaborative filtering. And we already discussed the general characteristics or the way they are handling this challenges. If you see this memory-based collaborative filtering, it mostly handles this influence of uncorrelated user service because it is actually trying to figure out the similar users, right? So
Yes.
it actually handles this influence of uncorrelated user service. On the other hand, this model-based collaborative filtering, for example, matrix factorization,
Hmm.
since you are uh, partitioning this matrix into low-rank matrices
Low rank.
and then reconstructing it. So basically, you are solving this data sparsity problem as well as cold start problem. So these two problem, and additionally, some of them actually solve this influence of uncorrelated user service. Add in top on top of this matrix factorization, they have added some of the memory-based collaborative filtering approach also.
Scalability also handling.
Sorry.
Scalability also been handled.
Yeah, scalability is handled because this number of features we don't need to deal with. Only
Yes.
the matrix we are dealing with, we are dividing it into low rank matrices. So
Load.
even the initial matrix is very high, you are dividing it into low rank matrix, then combining it and reconstructing it. So
Yes.
the scalability issue is also
Also
handled.
the result. Yes.
Okay.
Yes.
So you see different methods actually handle different challenges, but
Balance.
at the same time all the challenges are not handled by a single method,
Yes.
and
Yes.
that is going to be reflected in the results actually. Since memory based collaborative filtering, you see, they only handle this uncorrelated part. Compared to other methods, you see the MA is very high.
Yes.
On this case, actually, this model based collaborative filtering, some of them actually handled this outlier, some of them did not handle, some of them used actually MAC, some of them use this MAE as the loss function or Hubbard loss as the loss function.
Okay.
So when they are using MAE, they are using this modular value, not instead of square, so they are handling actually outlier.
Okay.
Hubbard laws actually, in some part it is using MSC, in some part of it is using ME. Okay, so
Yes.
it basically ensured this outlier resiliency problem. So as compared to them, actually, what we observed that ERRQP actually achieved a very good accuracy even for a very sparse data. You see,
Yes.
this for the 5% data, only 5% of the matrix values are available.
Yes.
Considering them, we achieved 0.3670
0.6.
as the MAE. So since it can actually address more number of errors, and that is why it is able to achieve very high accuracy. uh, Coming back to the response time and scalability part, so since the training of the model is done in offline mode, okay, so whatever user service information are available, we trained using those information, and later on we deploy this system and we use it for any unknown user service. We can actually predict what would be the QS value. So the prediction time is very less for this,
Yes.
and that is why it is very responsive system, and you can actually integrate it to the real time service recommendation framework. This is another advantage. Third advantage is the scalability. When we are using this feature vector, not only so here actually, this, as per your requirement, you can decide what would be the value of if that will be auto extracted feature, special feature. So if you want it very less, you can actually make it very less. On the other hand, here also for the initial embedding calculation also, we use this auto encoder to have this dimension very low. So the original dimension what we have used for our experiment is 155. And that is why, since the dimension is very low for each individual user service, so we ensure scalability also. So the three objectives which we defined here, accuracy, scalability, and responsiveness, these three objectives actually satisfied. We satisfied the scalability, this high dimensional data. We ensured that the feature vector size will be less by making it training it in offline mode. We ensure the responsiveness of our system is very high. Also, we address all the individual challenges, and we ensure the prediction accuracy is very high. And then what we did actually, we experimented it with TP dataset also, and we get the result in similar trend. What we observed in RT dataset, similar things has been observed for TP dataset also. And that is why what we can actually tell that our model is generalized enough that even if you apply in a different data set, there is a high probability that you will get the same results. Actually, we have done the statistical significant analysis to ensure this claim, but we did not include all those results as part of this presentation. So what we observed over here that this with the advent of service oriented architecture, this everything as a service paradigm is coming up, and becoming one of the key component in our socio-economy, influencing our socio-economy. And that is why most of the research attention nowadays is converting to everything as a service. So this digital twin, automated architecture, or the intelligent system, whatever we are doing, we need to actually ensure all this quality of service parameters. Web service actually are the fundamental component to enable this machine to machine communication. For example, what we established that one automated car requires this object detection algorithm. So it's a service. So it needs to communicate between multiple machines. So what is in front of you and what you are observing, all of them together, you need to infer what action you have to take. Selecting a service from a set of functionally equivalent services is challenging because various services are providing or ensuring various quality of services, various features, various cost. So trying to obtain this kind of optimal services which essentially satisfying a set of constraints is challenging. So this work which we discussed today is mostly focused on this QS aware service recommendation. We identified and summarized various challenges. This is not only true for the service recommendation, for any generic recommendation system. For example, I also involved in visual recommendation. For example, this movie recommendation from the posters or the trailer, or the book recommendations, or the product recommendation, Amazon or Flipkart product recommendation. For any recommendation systems, actually these challenges are actually a very critical thing which you need to address in order to achieve a very high accuracy. And we actually proposed one anomaly resilient framework for this QS prediction. And so currently what we are working on this latency optimization for the safety critical applications also. So this is the service part, and also we work on different platforms, multimodal recommendation system. I would like to thank my collaborators who are associated with this research, Dr. Chandranath Adok, who is an assistant professor in IIT Patna, and Dr. Aruni Bhattacharya, who is an assistant professor in IIIT Delhi, and of course my PhD student Suraj, who helped me to implement all these things, and some of the ideas came from him as well. And these are the few publications which we have done out of this quality of service prediction. So the first paper where we introduced this graph convolution neural network, which actually published in one tier A conference, ICSOC. Then we actually tried different component. We put them together and tried to solve different challenges of this QS prediction problem, and we came up with this FDQ framework. The CHP-HF framework, this paper being published in Transaction on Services Computing, it's an online framework. Even though the prediction accuracy is very high, but it's not compatible for real-time system. Today, I presented this ARRQP framework. A similar framework we have also proposed for temporal domain, for temporal QS prediction using multi-source collaborative features. Also, we have worked on another is the fast, efficient, scalable QS prediction framework. So these three works actually we communicated. So these are under reviews. So feel free to ask me any questions. So I have incorporated a few references if you are interested to look at for this service recommendation. Please feel free to go through these papers.
So,
Happy to take any questions.
okay, thank you, ma'am.
Yeah.
Thank you, Dr. Chattopadhyay, for an enlightening and informative presentation on service recommendation and QoS prediction using deep learning. Actually, really, it will be helpful to the peoples who are actually doing research in this area mainly. Actually, from my point of view, I enjoyed a lot. So I cleared some of my doubts and all. So
Okay, Okay, great. Later on also, if you have any question regarding the recommendation, you can feel free to drop me an email. I'll reply as soon as possible. I'm sorry, I'm not able to hear you. Yeah, now you are audible.
Okay, ma'am. Actually, there is some technical issue. That's why I'm not.
No problem, no problem.
Okay, ma'am. Actually, actually, I think will be look forward you for such type of events in near future, maybe. Actually.
Sure, no problem.
Okay, okay, ma'am. Actually, I want to know one thing. So, if you really recommend on QSA on the some on the basis of some pictures and all, what we have to do? We have to do study the images and all. After that, we can predict the QSA. Forward.
No, it's nothing about the image data. It's the numerical data we are handling currently. So
Okay.
this this response time is the time value, right?
Yes. Yes.
It's denoted in terms of seconds. So when we are providing this data, it's a numeric data represented in terms of a matrix.
Okay. Okay. Okay, sir.
So in different domain, actually you can have different mode of this data. For example, this movie recommendation system, you can have the trailer or the poster of the movie. So in
Yes.
that case, you need to deal with the image.
Image.
Sometimes you have this metadata, for example, cast and crew information
Okay.
or the director information. So in that case, you have to use this NLP for this recommendation. So the mode could be different, either numeric, or it could be text based, or it could be video or audio based. But
Okay.
the challenges almost they are same.
Okay.
And you can try with this kind of approaches. The model which we propose, they are generic enough, you can actually extend it. Once you extract the features from the image, you can use the same thing for the movie recommendation.
Okay. For the service of the quality of the service, for the like this suppose Amazon service and other web
Yeah,
based
yeah,
service only.
yeah, you can actually use them.
Okay. Okay, ma'am. Thank you, ma'am.
Also for the microservices, it is more actually makes sense when you have a multiple service providers, they're providing these services. When you have to do this thing, automatic traffic light detection, so there are many ways to detect this traffic. Many classifier actually they are implemented it using different classifiers. Many providers actually providing you in a different manners, where the reliability and the latency, actually you can see the trade-off. The one which is having more reliability may be having less latency.
Okay.
So when do you have to predict this? These are the real-time system for which you need to judge which service you have to take at what point of time.
Okay. Okay. According to time, what are the things you have to take? That is, you have to decide.
Not only time, it depends.
And the different parameter will be there.
Yeah, right. So it could be reliability, it could be availability of the service. So when you actually try to invoke the service is not available.
Okay.
So that should not happen. So so depending on various parameters, there are multiple parameters available by which you can judge the quality of a service. So any parameter works for this. So we tried with this for response time and throughput. These two parameters we tried with. You can try with other parameters as well.
Okay. Okay. Thank you, ma'am.
Okay.
Oh, ma'am. Actually, today is the concluding day of the FDP. If you will be,
Okay.
have some time, you can stay in the validatory system.
Okay,
Validatory
sure.
session. Okay. So now I would like to invite our director, Dr. Rajiv Khatri sir, to address the FDP. So over to you, sir.
A very good afternoon to all of you. My colleague, faculty members and dear students. Today I am pleased to be a part of this valedictory ceremony for this 7 days international FDP and workshop on deep learning and its application in emerging fields at Global. This FDP has been organized to bring people from industry and academia together for the mutual support, education, and inspirations, focusing on the development of an environment for the exchange of ideas towards technological developments for the benefit of students and the society at large. The plenary speeches by the experts on new technologies of computer from various IITs, NITs, and triple ITs on recent deep learning models for computer vision and various applications of deep learning, IPR, and other advanced research topics in AI, data mining, machine learning, etc., has definitely thrown new light on the developments in this field. I highly appreciate the efforts of whole of the organizing team under Professor Saurabh Sharma and Professor Vishal Paranjpe, Head of Departments of Computer Science and IT, and Dr. Mamta Samal for taking initiative in organizing this conference. Efforts of all the faculty members and students are also appreciated for their proactive participation. I extend my sincere gratitude to all our guest speakers for accepting our invitation to enlighten, motivate, and bless our faculty and students at this occasion. I once again express my sincere gratitude to all of you to this interactive program and wish a grand success to them for their future. Thank you. Jai Hind.
Now I would like to produce the report of the whole FDP. So we have done till now up to today. So good afternoon to all. A warm welcome to the validatory session. Respected director sir and HOD CSE Saurav Sharma sir and HOD IT Vishal Pranjpe sir and our HR Niharika ma'am and dear participants and my faculty colleagues and students. I am delighted to inform you that we have completed our second faculty development program on deep learning and its application in emerging fields. The last 7 days have been fascinating for all of us, not only for organizing the workshop, but also for learning different deep learning and artificial intelligence technique and their applications from experts. In day one, the Professor Dr. Venkatanaresh Babu from NIT Goa gave a talk on introduction to deep learning, where he briefly discussed about the neural network and its working. Then he covered persuasion algorithm and different neural network like CNN and RNN, etc. And also he addressed some of the questions of the MTech students. In day two, Dr. Nilkant Sahu from IIT Guwahati delivered a lecture on recent deep learning techniques for computer vision. In his lecture, he explained about the different algorithms used in the field of computer vision, like YOLO, GAN, and diffusion, and few set learnings. In case of few set learnings techniques, which makes prediction even with the limited number of samples and provides a clear vision of the computer vision. In day 3, Professor Dr. Ratikant Behra from ISC Bangalore delivered a lecture on tensor computation for data science. In his lecture, he discussed about the basics of the tensor and he mapped the tensor computation with the matrix computation. He also discussed about the fundamental operations on tensors. Along with that, he also discussed about how tensor is applicable for image processing and computer vision. In day 4, Dr. Sasekhar Jha from IIT Rupar discussed about the deep reinforcement learning and its application to the different domains like game, robot, ChatGPT, and so on. He also discussed about recent research papers on reinforcement learning. Along with that, he discussed about the different algorithms of RL like Q-learning algorithm, etc. In day 5, Dr. Swami Chattopadhyay from IIT Indore delivered a lecture on service recommendation and QS prediction. using deep learning. In hot talk, he discussed about different types of QS recommendation system, memory-based system, hybrid-based QS recommendation, and memory-based QS prediction. And along with that, she also discussed about the graph convolution methods, where I enjoyed a lot. And this is this is a great learning curve for all of us. This experience we gain from this activity will help us organize much more events in the future. This is not the end of the FDP, but the beginning of many more such future events. Thank you all once again for extending all the supports to make this event success. Now I would like to call Professor Neha Thakre ma'am to give vote of thanks.
So
Over
as
to you, ma'am.
So as we come to the end of this enriching and insightful online FDP program, I stand here with immense gratitude and sense of accomplishment. On behalf of Bateria Global Institute of Engineering and Management, I extend my heartfelt thanks to each and every participant, facilitator, and organizer who contributed to success of this program. A special thanks to our esteemed speakers and facilitators who generously shared their profound knowledge and expertise in the field of deep learning. I also like to express my gratitude to organizing team for orchestrating a seamless and enriching learning experience. As we conclude, let's carry forward the knowledge gained, applying it to academics and professional pursuits. Best wishes to all for continued success and innovation. Thank you.
Hello, ma'am, are you there?
Yeah, are you talking to me?
Yes, yes.
Yeah.
No, no, ma'am. Actually, if you share your slides, then it will be a great thing for us.
Okay, I can share actually.
You can mail to me also.
Yeah, sure, I'll do that.
Okay. Thank you once again, ma'am. To be back.
Okay, no problem.
Huh.